Welcome back to AI Paper Podcasts. If you're in AI, particularly machine learning, you've definitely seen this pattern, right? Bigger models, more data, more compute often equals these incredible jumps in performance. It's almost become a rule of thumb. But the big question for today's paper is, does this whole scaling law thing, which has totally changed the game for LLMs, does it actually work for something as, messy and critical as autonomous driving?
Yeah, that's the core question Waymo tackled. We're talking motion forecasting and planning here.
Exactly. Predicting where everyone's going, deciding what the car should do.
Yeah.
It's got inherent uncertainty, super complex interactions, real-time decisions with long-term consequences.
It's not simple stuff.
Not at all. So today we're digging into this really comprehensive study from Waymo. It's called Scaling Laws of Motion Forecasting and Planning. They basically set out to answer that exact question.
And their findings are, pretty significant for anyone working in AI, especially robotics. So for the quick summary, the kind you might need for a short clip.
Yeah, the 1-minute version.
Right. First off, yes, scaling laws do apply to AVs. Big takeaway. Motion forecasting quality gets better following a power law with training compute, just like we see with language models.
Okay, so the pattern holds. What else?
Second, data is king. Or queen, whatever. The point is, while the best AV models are surprisingly much smaller parameter-wise than LLMs, they need way more data to be compute optimal during training. They even found this specific ratio. Model size should grow about 1.5 times faster than beta set size for the best results.
1.5 times. Interesting. So smaller models, but hungrier for data.
Exactly. Third, and this is a big one, they showed, really for the first time convincingly, that getting better on those standard open-loop metrics directly correlates with better closed-loop performance. Think fewer failures in realistic simulations.
Okay, that is big.
Yeah.
Because there's always been that doubt, right? Does making the numbers look good on paper actually mean the car drives better?
Yeah, precisely. This study challenges that skepticism head-on. Fourth, inference matters too. You can actually boost performance just by making the model generate more possible trajectories at runtime by scaling inference compute. There's a trade-off with model size, but only up to a point.
More samples, better performance, but not infinitely.
Got it.
And finally, number 5, something really promising for robotics generally. They demonstrated that you can train a model effectively just by having it watch other agents drive around. Passive data. This skill seems to transfer to the ego agent, the AV itself.
Wow. Okay. That could be huge for data collection, which is always a bottleneck.
Definitely. It opens up a path to address those data challenges.
Yeah.
So yeah, that's the nutshell version.
That's a fantastic overview. Lots to unpack there. Okay, let's start with the basics. Motion forecasting and planning. What exactly are we talking about in the AV context? It sounds complex. How can we simplify it? Right. So motion forecasting, that's essentially predicting the likely future paths, the trajectories of all the dynamic things around the AV, pedestrians, cyclists, other cars. Where are they likely to be in the next, say, 5-10 seconds?
Predicting the future for everyone else.
Pretty much. And then planning, that's about figuring out a comfortable and crucially safe path for our vehicle, the ego agent. But, and this is key, that plan has to respect the route, obviously, but it must account for and react to all those predicted behaviors from the forecasting step.
So it's not just driving in a vacuum. It's constantly anticipating and reacting to this whole dynamic scene.
Exactly. It's super complex because, first, there's just inherent uncertainty. People don't always do what you expect, right?
Tell me about it.
Then you have these really intricate interactions. Think about a four-way stop, or a car waiting for a pedestrian, or merging onto a highway. It's complex.
Yeah, those nuanced social interactions on the road.
Right. And it all has to happen in real time, thinking about long-term effects in this continuous, ever-changing world. I kind of like thinking about it as this constant, silent dialogue between everyone on the road. The AV needs to anticipate, react, anticipate again. Like a really high-stakes, fast conversation.
That dialogue metaphor really clicks.
Yeah.
Okay, so given that challenge, how did Waymo actually build an AI model to handle this? What's the architecture look like?
So they framed it as what's called a conditional sequence generation problem.
Okay.
This is actually pretty common now. Think about how large language models work, generating text word by word.
Okay, so generating sequences.
Yeah. The architecture itself is an encoder-decoder autoregressive transformer, very similar to Waymo's earlier work, MotionLM. But here's the really clever bit, I think, and maybe a key takeaway for researchers listening. They figured out how to turn those continuous, smooth, real-world trajectories into discrete motion tokens.
Tokens.
Yeah.
So like words in a language model, but for movement. Instead of outputting exact coordinates, it's outputting. What, like turn left slightly, speed up a bit?
Exactly that kind of idea. It turns a really complex regression problem predicting continuous values into a more manageable classification task. Which token comes next? This makes sampling lots of possible futures much, much easier. And it's an approach that's worked well elsewhere, like in audio generation or even robotics control.
Smart. So it simplifies the output space. How do the encoder and decoder parts work then?
Right. So the scene encoder, its job is to digest all the input about what's happening right now. That's the road layout, the traffic light history, and importantly, the recent history, like the last 5 seconds of where all the agents have been. It builds this representation of the scene.
Kind of like understanding the current context.
Precisely. Then the motion decoder takes that scene understanding and starts generating the future, one token at a time for multiple agents. In this study, they focused on predicting for 8 agents simultaneously.
8 agents at once.
Yeah, autoregressively. So predicting the next step for Agent 1, then Agent 2, and so on, or perhaps predicting step-by-step for all agents jointly. It uses cross-attention to look back at the scene encoding, focusing on the relevant bits of context to make its next prediction. And it predicts pretty far out, 11 seconds into the future.
11 seconds is quite a horizon.
It is. And predicting for multiple agents jointly like that, it's a kind of basic form of what people are calling world modeling these days, understanding how the whole system evolves together.
Okay, makes sense. Now, you mentioned scaling laws depend heavily on data, and for this to work, you'd expect a ton of data. Just how big was the data set Waymo used here?
Oh, it was massive. You're right, data is absolutely foundational for this kind of study. They pulled together about 500,000 hours of driving data.
500,000 hours?
Yep. Curated from 5.6 million miles of driving. That boiled down to nearly 60 million unique scenarios or run segments and over 500 million training examples, just huge scale.
That's staggering. Was it just raw data or was there a focus on quality? Because garbage in, garbage out, right? Absolutely critical point. The quality was paramount. For this study, the training data consisted only of safety driver demonstrations, so human driving. No semi-autonomous or fully autonomous miles were mixed in for the core training set.
So high quality human examples is the ground truth.
Exactly. And diversity was key too. This wasn't just highway driving. It included really complex situations. Busy city intersections in places like San Francisco, Phoenix, LA, construction zones, dealing with emergency vehicles, freeway driving, those tricky you-go-I-go interactions with pedestrians and cyclists. You need that breadth to build a robust model.
Right, it needs to handle the messy real world. Okay, this is where it gets really juicy. What did all this data and compute actually reveal about scaling? Did the power laws hold up for AVs?
They really did. That's the headline finding. The loss function they used, cross entropy for predicting the joint future of those agents, it clearly followed a power law relationship as they increased the total training compute.
Okay, so more compute equals predictably better predictions following that law.
Yep. It extends what we've seen in language models and other generative AI right into the autonomous driving domain. It confirms that scaling compute is a predictable path forward.
That's huge for planning development. What about the balance, though? How much model versus how much data? That's always the efficiency question.
Right, and they had a really concrete finding there for what they call compute optimal training, getting the most bang for your compute buck. The ideal model size, NOPT, should grow about 1.5 times as fast as the ideal dataset size, DOPT.
1.5 times faster.
Yes, specifically the exponents were like NOPT proportional to compute 0.63 and DOPT proportional to compute 0.44. It gives a clear recipe for how to allocate resources as you scale up.
Interesting. And you mentioned earlier, kind of surprisingly, that these optimal AV models are smaller than LLMs. Can you expand on that? Why might that be?
Yeah, that was definitely one of the more surprising results. So, if you take the same amount of training compute, the optimal motion forecasting model they found is roughly 50 times smaller in terms of parameters compared to an optimal LLM, like based on the Chinchilla paper findings.
50 times smaller. Why?
Well, the paper offers a couple of hypotheses. One idea is that driving data itself might just require more examples to capture all the diverse, sometimes rare situations, rather than needing vastly more parameters in the model itself.
So the complexity is more in the data distribution than needing a huge knowledge base.
Kind of. The other thought is that driving intuitively might rely less on that sort of broad knowledge retrieval that LLMs are good at, and more on immediate spatial reasoning and interaction understanding. Maybe that just doesn't require as many parameters, especially in the feed-forward layers of the transformer.
Fewer parameters, but maybe a bigger appetite for data. That's quite different from the LLM narrative sometimes. What are the practical implications then?
Well, first, it really underscores how critical data collection or finding smarter ways to use data is for AVs, maybe more so than just chasing parameter count beyond a certain point. And second, a nice side effect. Smaller optimal models generally mean lower latency.
Which is crucial for a car making split-second decisions.
It's absolutely vital. They also noticed something interesting about the loss curve. It seemed better fit by a power law plus a constant. This raises a question. Are they hitting some kind of fundamental limit, like the true randomness or entropy in driving? Or is it an artifact of the data set size? Or maybe limitations in how perception data feeds the model?
An irreducible error floor, perhaps.
Yeah.
Fascinating question for future work.
Definitely.
Okay, so the scaling laws hold for the training metrics, but what does that actually mean for the car driving better? Does improving laws translate to a safer, more capable AV in practice, or at least in realistic sims?
Yeah, this is maybe the most impactful part of the study. First, they confirmed the basics. Improving that cross-entropy loss did lead to consistent improvements on standard open-loop metrics. Things like MINAID and WAA, minimum average displacement error, weighted average displacement error.
Right, those measure how close the predictions are to what actually happened.
Exactly. How far off the predicted paths are from the ground truth. So better loss, better open-loop predictions, that lines up.
But the big hurdle has always been translating that to closed loop, right? Where the model's decisions actually influence the simulation going forward. People were skeptical if open-loop gains really meant anything there.
Totally correct. That skepticism was, and maybe still is, quite widespread. Prior work sometimes showed a disconnect. You could improve open-loop scores, but the simulated driving didn't necessarily get better, or could even get worse with imitation learning.
So what did Waymo find?
This is the breakthrough. Because their study was so controlled, simple architecture, simple loss, focusing only on the effect of scaling, they showed, pretty convincingly, that closed-loop performance also scales. Specifically, they measured the number of simulation failures, like collisions or driving poorly.
And those failures went down as compute went up.
Exactly. They followed a similar scaling trend. More pre-training compute led to fewer simulation failures. It suggests that investing in scaling the training directly improves the simulated driving capability.
Wow, okay, that is a game changer for development. It validates the whole scaling approach for safety-critical systems in a way that maybe wasn't clear before.
Precisely. It's incredibly promising. It means you can pour resources into scaling data and compute for this supervised task and have confidence it's actually making the simulated AV perform better and safer. They did this by taking their pre-trained models, fine-tuning them slightly to output plans specifically for the ego vehicle based on a route, and then running them in a closed-loop simulation with other reactive agents.
And tracking things like collisions or deviating too much from human driving.
Yeah, or not making progress or causing problems. Failures decreased with scale.
Okay, so that covers training scale. What about when the car is actually driving? Real-time performance and efficiency. You mentioned inference scaling.
Right. So separate from training bigger models, you can also improve performance at runtime during inference just by using more compute then. The main way is by generating more samples from the model. Instead of just predicting, say, 8 likely future scenarios, maybe you predict 100 or 1,000.
Exploring more possibilities.
Exactly. And they found doing this significantly improves performance, better coverage of possibilities, measured by MAP, and better precision, measured by things like minimum final displacement error, MINFDE, or MINE again.
So a smaller model working harder at inference time could potentially match a bigger model that's doing less work. Is there a limit?
There is. They found this really interesting crossover point. Yes, a smaller model sampling heavily can compete with a larger model sampling less, but only up to a certain level of performance. Beyond that crossover, the larger model actually becomes more inference compute efficient. It gets better results for the same amount of runtime compute, even with fewer samples.
Okay, so you can't just sample your way out of needing bigger models eventually.
Seems not. It suggests we need both. Keep training larger, more capable models, but also develop smarter, maybe adaptive inference strategies. Imagine the car deciding how many samples to generate based on how complex the situation is.
Right, simple highway, maybe fewer samples, crazy intersection, crank up the sampling.
Exactly that kind of dynamic adjustment.
This brings up that data point again. Collecting AV data is notoriously hard, expensive.
Yeah.
Safety drivers, specialized vehicles.
Yeah.
You mentioned earlier this idea of learning from passive observation, getting more mileage, pardon the pun, out of existing data.
Haha, yeah, it's a huge challenge in robotics, right? Getting enough high-quality demonstration data for these big models is slow and costly. So Waymo did this preliminary, but I think very cool study. They trained models only on predicting what other agents in the scene were doing: pedestrians, other cars, cyclists. They specifically excluded the ego vehicle, the AV itself, from this training data.
So the model just watched everyone else drive.
Essentially, yes. And then they tested it zero shot, meaning without any further training on predicting the trajectories of the AV ego agent.
And did it work? Can you learn to drive just by watching?
Remarkably, they found it showed reasonable zero-shot generalization. The models trained only on observing others could still make sensible predictions for the ego agent, and importantly, this capability also followed similar scaling trends with compute.
That's amazing. So observing others transfers skills. Did they quantify it?
They gave a preliminary estimate. Roughly speaking, observing 10 miles of driving from other agents seemed to provide the equivalent learning benefit of about 2 to 3 miles of direct demonstration data from the ego agent itself.
Wow, a potential 3x to 5x multiplier on data value just from passive observation.
Potentially, yeah. Now, there's a caveat they mention. All this data came from their own AV platform logging everything, so there might be some correlation between the observers and the ego vehicle's context. It's not quite the same as just learning from random dashcam footage, maybe.
Okay, fair point. But still.
Still, the implication is huge. It points towards a powerful way to help overcome the data bottleneck in robotics. It could make AV foundation models more generalizable, maybe helping them adapt to new cities or driving styles without needing massive new data collection campaigns everywhere.
Okay, zooming out then, what's the big picture here? What does this study really mean for the future of autonomous driving and maybe even AI and robotics more broadly? It feels like we're moving towards a more predictable science of scaling these things.
I think that's exactly right. These empirical scaling laws, now shown to hold in this complex domain, they offer a much clearer, more systematic roadmap for improving AV performance. It's less guesswork, more predictable engineering.
And that correlation between scaling and actual closed-loop performance.
That's the linchpin, really. It's a game changer for development confidence. Investing in compute and data now has a much clearer link to achieving better, safer, simulated driving. Add to that the insights on optimal model data sizing, the inference trade-offs, and this potential for leveraging passive data. These are all concrete levers we can pull to keep pushing AV capabilities forward.
It really does feel like a significant step in understanding how to build these incredibly complex systems.
Absolutely. And what's truly fascinating, I think, is that while this is obviously pushing AVs forward, the underlying principle might be much broader. If these scaling laws, these predictable relationships between data, compute, and performance turn out to be this universal, it makes you wonder, right?
Wonder what?
What other really hard, seemingly intractable problems, maybe in robotics or other complex domains, could we start to systematically crack just by applying this scaling recipe, investing strategically in data and compute, guided by these predictable power laws? Where else could this approach unlock breakthroughs?
That is a really powerful thought to end on. What other complex systems might yield to this kind of systematic scaling?
Fantastic. Well, thank you for walking us through this fascinating Waymo paper.
My pleasure. It's really important work.
For everyone listening, you can find a link to the full paper, Scaling Laws of Motion Forecasting and Planning, in the description. Thanks for joining us on AI Paper Podcasts.